My name is Alon, and I'm going to talk a little bit about our attempts to design a RISC-V based graph processor, which means a processor that processes graphs better, not a graphics processor, which sometimes people get confused. So for the less hardware-inclined people, a little bit about the Berkeley approach to open hardware. So one of the agendas the Berkeley Architecture Research Group is trying to push is open source hardware development to kind of drive hardware innovation with a larger community and not be limited to simulators or Intel and ARM creativity. So some of the stack is RISC-V, which has been externalized, and it's an open and free instruction set like ARM, like x86, but now everybody can use it. Chisel is a high-level hardware description language, so it's not high-level synthesis. It's like Verilog, but it gives you a lot more tools, a lot more parameterization capabilities, and use of high-order functions and other things you can use in managed languages. And the Rocket Chip generator, which is basically a generator written in Chisel that you can configure and parameterize cache sizes, cache parameters, accelerators, anything you want to add in your chip. So it generates system-on-chip Verilog, and we can later synthesize that to physical design. Next steps are automating physical design and continuing with the open source approach. So why are we doing this? Because we tape out a lot of chips, because we like to prove our things in hardware rather than just simulating them. And it also proves the agile approach that we're advocating for using those open source tools, that you can iterate and try new architectures in recently fast times. So about 2 chips every year, which is for using a 4 to 6 person group is quite well, I think. So why do we need to try all these new things? Because in hardware, we are kind of limited in the advancement of CPUs. So we're going for the accelerator approach. We're making different chips for different purposes. So we mostly know about the FPGA and GPU, but recently we had the TPU that came out from Google. We have codecs and crypto accelerators. We have Intel's vector accelerators. So we're basically, instead of continuing with the single-thread general-purpose processing approach, we're splitting up into domains. And so when we split up into domains, one of the domains we thought about, and a lot of people have thought about, is graphs. And we think about it especially when you're DARPA funded. So why graphs? Because you can apply graph algorithms to a variety of different fields. So you can apply them to genomics, you can apply them to networking, you can apply them to fraud detection, social network analysis. So a variety of fields represented using some common data structures and common algorithms. These are just some examples. I won't read all of them. So why are graphs considered a problem in computing? Generally, we consider 2 major problems. One is the data layout. Computer architects love spatial locality because entering DRAM takes time. You need to activate rows. So you like that everything is next to each other. So you can prefetch, you can batch, you can do a lot of things when you know what you're bringing in. The problem with graphs is you have a lot of different connections. Things are not laid out next to each other, which causes a problem. The second problem is implicit data level parallelism. So when we do a dense matrix multiply or other data parallel activities, we know how to block them, how to partition them well to run them fast and parallel. In graphs, the parallelism is a little bit less exposed, so it requires a bit more work to expose it. So this is an example of a way to address the data layout. So the way we represent graphs usually is either an adjacency list or an adjacency matrix. The computer architects usually won't like the adjacency list because it's a lot of pointer jumping. So I mentioned spatial locality. A list doesn't have any spatial locality because a pointer can point to a totally different location in memory, which will take time to fetch. There are some optimizations to adjacency list which try to block edges together, and they were done in Georgia Tech and Tokyo and Livermore. But the most common graph representation is an adjacency matrix because we can represent them as sparse matrices. And sparse matrices, we know how to compress, how to represent them in more efficient ways. So a very popular one is compressed sparse row, which basically takes the rows and compresses the zeros out of them. Another development on top of it was doubly compressed sparse column, which says we can also compress the column if the matrix is sparse enough. Coordinate format, which gives you the list of edges in coordinates, which is a little bit less popular, but can be addressed in dynamic graphs. But these are the approaches for high-performance graph processing usually. When we talk about exposing parallelism, the nice people in the systems world came up with a bunch of different abstractions to expose the parallelism in graphs. So a popular abstraction that was popularized by Google in their pre-Go framework is the vertex-centric, which basically means I write a program for every vertex, and I will run it for every active vertex. So if we take a BFS, for example, if I'm the vertex, I look at all my incoming edges. I check the minimum BFS level, and if it's smaller than mine, I look at my outgoing edges and I activate them. Similarly, for shortest path and PageRank, you can write different programs. A different approach is the sparse linear algebra approach. Because we know how to do BLAS, we have a lot of techniques for sparse linear algebra. So a recent standardization attempt called GraphBLAST tries to frame graph algorithms as sparse linear algebra formulations while overloading the multiplication and accumulation. So again, if we look at a BFS, then I can multiply the active vertices with the adjacency matrix when the multiplication is a minimum and the addition is a minimum and the multiplication is a +1 to the previous BFS level. So all these solutions were proposed by the software people. And the systems community really likes this graph problem. This is a survey that was done by Delft in 2014, I think, and I can guarantee that the number of frameworks has doubled since then. So there are a variety of graph frameworks for a variety of environments and reasons. So these are examples of just some of the popular ones. So I mentioned Prego, which was kind of the first one popularized by Google. Then, of course, everything Google does, there's a Hadoop equivalent, so we have Giraffe. And then when we have a Hadoop, we have a Spark equivalent, so we have GraphX. So those are mostly the distributed ones. We have the shared memory frameworks. We talk about Ligra, GraphMat, Galois. They use somewhat different abstractions. GraphLab was very popular in 2012. And then we have frameworks that also look at secondary memory. So they go down to disk, they go down to SSD. So Mosaic got a few headlines a couple of months ago because they managed to process 1 trillion edges. We have Extreme. But again, a really big variety of software frameworks. Just a side note, there was a nice paper in HotOS in 2015 that showed that for most of the frameworks back then, you could get faster results using a single thread on a laptop. Which means that while it's a very interesting research topic from a systems point of view and a scalability point of view, you really need to pick your solution correctly based on your data set and based on your problem. So we took two of these frameworks, two of the high-performance shared memory ones, because distributed are a bit harder to analyze, and we tried to look at their memory access pattern to try to see what we can do with the memory system. So we took Ligra and GraphMat, which use a bit of different abstractions. Ligra is more vertex-centric. GraphMat uses a sparse linear algebra backend. Even in the parallelism, they use kind of different granularity. GraphMat, as a sparse linear algebra abstraction, uses more coarse-grained parallelism, while Ligra uses OpenMP for loops. And even the memory access optimizations were different. GraphMat used bit vector predication, so they can access all the memory sequentially, while Ligra decided to sort stuff depending on the size of the frontier of the traversal. So this is kind of a zoomed out version of the memory access pattern trace. It's not to scale at the moment, but just to show you that when you look at two different frameworks that do the exact same thing, it's a BFS on a Higgs Twitter graph, which is about 500,000 vertices. And the memory access pattern is quite different when you look at it from far away. So if we focus on the Ligra one, first of all, we can see that the edges comprise most of your memory footprint. It's about 5 times more than the vertices. And we can also see that the edges are usually accessed only once, so there is no temporal locality here. While the vertex properties may be accessed a few times. We can also see their approach to memory access optimization when they sometimes sort the vertex properties and sometimes the vertex properties are unsorted, depending on the size of the frontier of the graph. When we look at GraphMat, on the other hand, first of all, we can see that the vertex properties are split into 2 different bands. This is because the linear algebra abstraction uses a y equals ax, and the ax and the y are vertex properties, depending if they're active in the previous iteration or the next iteration. But we see it's a lot more regular. You can see the coarse-grained blocking that GraphMat uses. But again, we can see that edges are accessed with no temporal locality. This time also the vertex IDs are accessed with no temporal locality. And it looks nice from a zoomed out perspective, but when we zoom in, we can see the problem that we always have with graphs is that eventually we will have a random axis because we still need to traverse the graph and access at least one random vertex property. So what can we learn from that about our choices for designing an on-chip memory system? So when we look at the cache versus scratchpad domain, for those of you who don't know what's a scratchpad, it's kind of a memory that doesn't remember temporal locality on chip. So we thought about a bunch of different solutions, perhaps partitioning the cache for vertices and edges, because obviously we don't need to cache the edges. So for that, we can use virtual local store, which was something that was proposed a few years ago about dynamically partitioning the cache to turn some of it to scratchpad. We also thought about fine granularity caching, because vertex IDs and edge IDs are usually small, so we don't need the entire 64-byte cache line. We can use smaller elements. And prefetching, which is a very wide research area in computer architecture in general and in graphs in particular. I think there was a paper from Technion a couple of years ago from the Pellet about context-aware graph prefetching. So you can talk about strided prefetching, which is very good for GraphMat, for example, because it uses bit vector predication. You can talk about data structure prefetching, which I'll mention in the next slide. But you also need to consider whether you want a dedicated hardware prefetcher, or at some point it becomes, the traversal of the graph becomes so complicated that you will want a small core that will run prefetching separately. I mentioned data structure prefetching. Just in a couple of words, what it does, it basically snoops the data cache in order to identify the indirections in the sparse matrix data structure and prefetch the next indirection. So if I have a CSR format that points to a different array that points to a different array, based on the first array, I can snoop the cache and prefetch the next array and the next array. It was proposed by MIT in their IMP paper. It was proposed in a couple of papers. Mostly these solutions are similar, but they take a different approach to finding out the address bounds, whether to detect them automatically, how to time it, what's your prefetching distance. But it's generally a popular idea in this field of difficult data layouts, and we will probably use it as well. Our approach to parallelization is vectorization. So for those of you who don't know, Berkeley really likes the old-style Cray vector machines, and that's also the RISC-V vector extension proposal. So basically, instead of using packed SIMD like Intel, AVX 4 elements, 8 elements, 512 elements, the vector machine approach gives you a more generalized view of vectors, and the code remains the same while the hardware is different. The reason to use this is because it was already found out that not in all graphs are not memory bound in all cases. In some CPUs, they're compute bound. So there was raw pressure characterized on x86 Ivy Bridge. A bunch of other papers proved AVX is very beneficial. GPUs have been shown to be memory bound, and gather is the real key cross point between the sparse data structures and the actual packed vectors that you need, and it's an area we need to focus on. So just a recap of our current approach for the irregular memory accesses, prefetching and partition caching. For the implicit data level parallelism, so integration with a nice framework, and vectorization using the RISC-V vector processing. So some of the existing solutions in this area. So in the software world, I mentioned the graph frameworks. I mentioned there's a whole lot of them. But there are also a lot of hardware-dependent algorithmic optimizations. So another work from Berkeley a few years ago was direction optimizing BFS, which kind of did a top-down, bottom-up approach to BFS to kind of reduce memory accesses. There was work from MIT this past year about clustering vertices that are accessed frequently in order to keep them in cache and not keep other elements in cache. There are also software frameworks that say we really know how to use our hardware and we will wrap it up in libraries for you. So Ligra actually uses compare and swap atomics and more basically bare metal primitive. Grazelle wrote a lot of their work in assembly. So those are mostly the software approaches. In the hardware world, we have massive multi-threading, which Cray does it great, but they're very expensive. We have GPUs that are very popular, but recently had a lot of problems with moving memory from main memory to GPU memory and load balancing because they have a lot of control divergence. FPGA libraries are also very popular, but their performance is sometimes comparable to CPU, so they aren't always being used. Two approaches that have been shown in simulation are processing in memory, which basically means having a little logic core in your big memory chip and communicating between those logic cores using some put-get interface. And a lot of papers about basically algorithm-specific dedicated accelerators. So basically having a nice pipeline that does a BFS really fast or a PageRank really fast. Now, these architectures are generalized, but their performance is shown based on some fixed function. So there was Grafiscinato in Micro and another architecture from Intel at ISCA a couple of years ago. So some of the insights when you look at all this previous work and all these challenges is that there are really a lot of proposals, but very little adoption when you look at the market. So when you look at previous work in the world of fixed function accelerators, they show an order of magnitude of improvement. But when you talk with application people or system people about graph processing, they say, what can we do with one fixed function? So you can do a BFS really fast. What can I do with this? I usually need to do something while I do a BFS. I usually need to do a PageRank and some community detection. I need to do something more complex. When you look at a lot of the software techniques, they're mostly used in the HPC community rather than the entire distributed systems graph framework world. When you look at your data sets, so we talked about that cost paper earlier. That's because most of our data sets fit in memory of a modern server. So they're a few tens of gigabytes. But if you look at graphics or Giraffe, they're meant for distributed systems. So it's no wonder that a single thread in a laptop is better. When all of our data sets are fit in memory, it becomes really hard to solve the real problems of distributed graph processing. But when you ask the big companies, the cloud companies, do you have a problem with graphs? They say, of course, we have a huge graph that's 4, 5, 6 terabytes or even more that doesn't fit in memory. So we're basically communication bound. So what are you doing solving us on-chip memory and little tricks? So some people, like the Mosaic paper, solved that using synthetic data sets, and they claim that the distribution of vertices is the same as the distribution of a real data set, but it's still very hard to prove because graphs have a lot of properties that depend on the origin of the graph. A little bit more, so end-to-end performance evaluation. If you look at most of the graph papers, a lot of them ignore a little thing called graph construction. So if we refer again to the Mosaic paper, which showed 1 trillion edges, BFS in an hour, or a PageRank iteration in 2 hours, they also mentioned in their paper that the graph construction took 30 hours, which I think is 5 or 6 times the time of the actual graph processing.
That's one-time cost, right?
So that's the question. Do you construct the graph only one time? Because when you ask most of the cloud providers, they have some dynamic graph that they take snapshots of. So that turns it into a totally different problem. If you look at the GraphX versus Ligra or versus Cost again, so GraphX showed that they're slower than, in their original paper, they're slower than GraphLab, they're slower than another framework, but when you measure end-to-end performance, meaning from the data to the result, they showed that they get better results than these frameworks. So the measurement here has a really wide variety that's very hard to compare. Another small insight is that people don't distinguish between graph processing and graph serving. So graph processing is usually based on the statistics of the graph topology, graph structure. Graph serving is more like Facebook graph search, a lot of content-based, database problems. That's not what we're doing. And that high-level framework integration with hardware is not always good. So we did an experiment about using a data structure prefetcher with GraphMat. And we got an improvement, but we also got a huge improvement with a strided prefetcher. And the improvement between a data structure prefetcher and a strided prefetcher wasn't that big. So sometimes it's better to just use a strided prefetcher if your framework is designed well enough for it. So some of the challenges we have are the lack of performance-bound graph applications to use. So we have those data sets, but we don't know what are the applications that we're trying to solve for. When we're talking about benchmarks, a very popular benchmark in the graph world is the Graph 500, which is a BFS. But again, what can I do with a BFS? That's how we come up with a lot of solutions that can't be used for anything. And it also, I think it also measures graph construction, but there is still a wide variety of benchmarks that are not application-driven, they're kernel-driven. So we get a great result for the benchmark, but nobody can use that domain-specific accelerator or that fixed function accelerator. Also, when we talk about graph processing in general, so we saw that a lot of problems can be represented as graphs, but when we try to solve all of them together, we basically get a very small improvement compared to a general CPU. So if we try to split the problem into more subdomains of graph processing, I believe we can get better results. And just as an example of splitting them with different characteristics, so we have some problems that are iterative, some have a single source input, some have a graph input, some have fine granularity memory accesses, some of them don't. Some of them are bipartite. If I only handle bipartite graphs, I can partition my memory even further and have better accesses. Some problems are NP-hard. I'm not sure I can do much with that using hardware acceleration. So I believe that if we define our problem domain more specifically while not being completely fixed function, I think we can get better results. And finally, our last challenge is utilizing our infrastructure advantage. I'm not going to compete here with an Intel Xeon Phi or a new NVIDIA Volta, but we need to demonstrate our ideas, still using hardware because we usually show better energy efficiency. We show a variety of characteristics that we can show only with hardware, but still demonstrate these ideas using simple chips, using our memory interfaces, usually serial links or a simple DDR, and trying to integrate new memory technologies using our real tape-out capabilities. So just to summarize what I talked about, we can represent a lot of problems as graphs, data level parallelism, and irregular data layout. We don't have performance-bound applications to analyze. And with the abundance of software frameworks, the question is hardware acceleration of graphs justified? And I do not have a complete answer on that yet. Thank you.